Alright, good day guys. How are you all doing? Talking about Coulombs law. And under Coulombs law, we mainly fix some principle of what we call superposition. And right from when you guys could understood from Coulombs law, we know when you talk about Newton's law of gravitational motion, it deals with a particular mass of certain particular objects which attracts. And when it comes to what do they call it? Coulombs law. Coulombs law performs to certain particular category, which Newton's law of universal gravitational cannot. Universal gravitational deals with only law of attraction, but Coulomb's law actually talks about both the law of attraction and repulsion. Now, when it comes to gravitational field, that's universal gravitational field, that one mainly deals with masses of a certain particular object, while Coulomb's law talks about charges. So there are some certain things we need to know before we move on into what we call principle of superpositions under Coulomb's law. And we all know the particular certain definition of Coulomb's law, which says the certain particular force which is applied on certain particular charges. The attraction or the repulsion between certain particular charges deals with a particular force, which varies directly as the product of the charges, and also inversely as the distance between them being apart, or the distance squared between them apart. And you should know that for every variation there is a constant of proportionality. Now, why is this value there? Is that whatever force you are looking for, a normal literal force, this is a normal force, not in the vector level, or let me just say not in like the horizontal aspect. So a normal force you are looking for with the formula, even though you have a negative charge here, it has to change to positive because of these two things you see. We call it an absolute value of charge. So if your force is being given to you, even though let's assume we say Q1 is negative 234, if you want to put it into the air, it has to function as normal 234, not minus 234. So and we have our k, which is known as the constant of proportionality. You know, there's for most, like I said, for every variation there's always a constant of proportionality. Now this k is also linking into a certain particular formula or a certain particular let's say illustration, which is 1 over 4 pi permittivity of free space. Now whatever we are dealing with most of the times, we are dealing with a dimensional plane which happens in a space. So most of the times we have our permittivity of free space, or say the permittivity of the constant value, which is 8.85 times 10 raised to power minus 12. Because at times it might be breaking down in some aspect whereby you need to start reshuffling them yourself to get your answers. So what do you want to talk about without no much ado to start stressing and breaking things down in a way that it feels complicated? We just need two things to understand here, and the next them what we just need to understand. Now what do we need to understand is that when you talk about superposition deals with multiple charges, a source charge. You get, because Coulomb's law at a normal level talks about two only particular charges, while superposition makes you or allows you to explore much more, having a series of charges. Now, looking at this diagram now, you see you have a particular charge here. Now, this is just like an assumption. All this now, we haven't actually say, okay, this has a certain particular charge of this. We are just using an illustration to explain how some charges in different them works. Now, we have two things we need to take note of when we are dealing with superposition. We call it source charge and test charge. Now, you see this source charge, they are like I said, from a certain assumption. This source charge, we assume them to be like a charge that is fixed in one position. So, that actually their position is constant. Now, what these are examples of the source charges. Your charge 3, your charge 2, your charge 7, and this. These are an examples of a fixed point of charges. Now, we have another one called test charge. Now, the test charge is the one that we allow for it to move. Now, it can also be called the point charge. Are you getting what I'm saying? It can also be called the point charge. Now, from this point, we already know two things, that source charge are charges that are fixed at a point. But what is now the relationship between source charge and test charge? And what is the particular direction at which they move? And what is the force that binds them together? And stuff like that. That is another thing we want to explain to ourselves. Are you with me? So I feel like this is the first part we need to understand and get a clear intuition of. Now, you see, we call this a unit vector. For every movement of a certain, now most cases at times, you guys, if you get to a certain particular advanced textbooks, you will see whereby you'll be given this as a unit vector showing the direction of every particular force. illustrating force even as a particular vector, because literally is a vector. Are you get what I'm saying? But so as not to make things complicated, we can easily just omit it. Are you get what I'm saying? So let's proceed to the next step and try to get one or two things that we are trying to explain to ourselves. Now let's make some one or two let's break some certain things down under this diagram, as you can see. Now we talked about Coulombs law. We said under superposition, right? And there's something which I told you guys is that you have Ri as like a unit vector which points in the same direction. Now let's discuss the whole lot of nonsense that we have here. Now it tells us that I don't actually just want to start writing. Literally, we could actually say this orally and explain it. Now we should know that the test charge would be exerting a particular certain force on the source charge. Are you guys what I'm saying? And we told you guys that we just made an assumption that let's assume that these source charges are fixed and these test charges are the one that can move from a certain particular place to another. That means that since these ones actually can't move, they are fixed, they would be applying a certain particular force on this one. We are just making an assumption now. We call it a force of either attraction or repulsion, but basically we all take this as, let's assume this is what this is applying, or this is actually putting a certain particular force of attraction towards this test charge. That means you have charge 1, a force of attraction, and if you look at now, you are going to have in the direction of what? Under the charge 1, moving through the particular charge. You also have charge, the charge 2 charging toward the test charge. You have the direction 2. Then charge 3 also does that. Charge 4 also does the same thing, and the rest. Now look at what we want to try to break down from here is that now there's something we talked about unit vector, is that unit vector will point in the same direction. That's this certain unit vector you are seeing. As you can see, the unit vector 1, unit vector 2, they will all point in the same certain direction. Are you getting what I'm saying? To your charge 3, you have this movement of the 3. Your charge 4, you have R4. So like that, they will all point. Now, if you look at how can they point? This is like a theoretical thing. This is just like me breaking a certain thing down for you. But in a normal theoretical level, the unit vector will point in the same direction. Now listen to something now. Before I now move to the definition and the particular thing we want to break down under the superposition. Now, we say that we know that the unit vector actually points in the same direction, right? But the force, that's what you're moving to now. The force can be that of attraction. Are you get what I'm saying? And in terms of the force being attracting, it has to depend on which direction is the force going to move. Are you with me? So if it's the force moving in the particular positive direction or the negative direction, though they have attracted. Are you getting what I'm saying now? So even though the distance, or let me just say the direction is the same thing. Are you with me? They have the same direction, because when the charge is coming out, know that this one also, if it wants to come, it has to attract this one individually. Are you getting what I'm saying? So their distance being the same thing. Their distance being the same thing doesn't mean that the force between them will also be the same thing. If someone decides to have a force of positive, moving towards the positive direction, this one might decide to have a force of what? Negative, moving towards the negative direction. Are you getting what I'm saying now? So they say that what the force vector might not be what? Might not be equal. That means it might not point in the same direction of that unit vector. So that means my force points in the opposite direction. Now, we know that, like I've said, that what? Source charge. This is our source charges. We also exert a force on the test charge. This is the charge we are testing. So since we know force charge will exert a particular force on the test charge, we also know that what? The test charge will also exert a force on the what? On the source charge. Are you getting what I'm saying now? So in that point now, just like we say that it can also exert an equal, the same charge, the same force. It can also exert the same force. But whenever it is exerting that particular force, at that point, the force might be equal. That's the certain particular force might be equal truly, but it might be in the opposite direction. Are you getting what I'm saying? So the next thing does that means that what? Source charge can also change position. Like I said, it can also change position. But we assume it to be fixed so as to get the point that we need. Are you getting what I'm saying? So from there now, we say that what? If we assume for source charge to be fixed in one place, that means that somehow that their position will be constant. So if their position is constant in time, Then we now allow test charge to be moving. That means what? The analysis of this particular point at which the test charge is moving in order to attract the source charge at a fixed point. In that process, we call it what? And it's the point whereby this is is applying an electrostatic force. Are you getting what I'm saying? So, from what are we trying to discover? What are we trying to explain is that this is just like we basically are assuming some certain things on how the charges are going to relate to themselves, and the distance, and also the net force, which we know as like the resultant force. Are you getting what I'm saying? So we have to note some certain things. Now let's now move to the definition of what this man is telling us here. Now it tells us that under Coulomb's law, it says when two charges exert a force together on the third charge, when two charges they do what? They exert a force simultaneously the same time. Now if you look at, let's take a look at charge 1 and charge 2. Now let's assume they exert the same force now the same time on this test charge. This is the third charge. Now if they exert a particular what do they call it, a particular force simultaneously to this test charge, are you with me? It says that the total force acting on that charge, that means that the total force, the totality. Now you know this is a particular first force. Now force 1, you have force 2, you have force 3, force 4, force 5, like that. But we are not going to categorize it that way. We can say this point charge now we have its own specified force. So with each charge applicable to it. Are you getting what I'm saying? This is a particle, these are also particles. But let's now take it the normal way that we are saying that what? The total, if you want to get the total force of those two particular, what do they call it? Those two particular charge, which they are acting on the third charge. That's the force they are applying on the third charge. If you want to get it, you have to add all the particular force together. That's the force on the first charge applying on that third charge, and the force at which the second charge is also applying on the third charge. Now look at what it means. I said the total force accounting on the charge is the vector sum of the force that the two charges will exert differently, individually. Not that because charge 1 and charge 2 exert the force together, that means they both have one force like that. No. Charge 1 force will be considered as one part. Charge 2 force on that test charge 2 will be considered as one part. So if you now want to get the net force, you'll be adding the force of charge 1 and force of charge 2 together, and many more. If it's to like 8 now, you add them all together to get the total particular charge. That's the total force rather. That is what? That the particular charges have been acting on the test charge. Are you getting what I'm saying? So this phenomenon is what we know, or what we call the principle of superposition. Now look at a little illustration of what we are talking about. Look at, let's say that we have a certain number of source charge, like we know we have charge 1, charge 2, like we are explaining here now. Let's say we have a certain number of charge particles, a lot. If they interact differently, independently, they don't depend. If they interact independently in pair, this one, charge 1 pair with test charge, charge 4 pair with test charge, like that. Now, the force on any one of them, let us say that we have particle 1, and let's say that particle 1 is our test charge, like the way we were talking about. So that particle 1 is our test charge now. You should know that if you want to find the vector sum of all the particular other charges, let's say the charge, let's say it is also a charge, but the moment force are being acted on this charge, that charge will now become much more like we say a test charge. You get? So it will be different from every other charges. So at that point now, charge 2, are you get what I'm saying? Charge 2 would be applicable to charge 1, charge 3 would be attracted to charge 1, charge 4 will attract charge 1, and like that till the total number of the sources charge that you have. So to find the total charges is the addition of individual of them, the force at which individual of them act on that particular charge. So that is why if you look at now, let's say that you have force of 1, 4. This now, if you want to pronounce it, is you are going to say the force acting on particle 1. The force at its what? At which charge 4 is being acted on particle 1. This is the presence of what? This particle 4. Are you getting what I'm saying now? So in a more theoretical, then when example is being explained and being explained, I feel like we would have much more intuitive understanding on what we are trying to break down here. Are you getting what I'm saying?